Can you hear okay?
Yep. I can hear you.
Okay.
You can hear me?
This is good. So we are, here's Mike from the Tor Project, and I'm Seth from EFF. Mike is going to give most of the presentation talking about a lot of the motivation for reproducible builds and a lot of the work that a number of projects have done in this direction. And I'm going to talk about a particular demo that I think really focuses on the motivation and why we care about this problem for security. So we have a number of people. Mike, would you like to describe who all the people are?
Yeah, so obviously a lot of work has gone into this problem over the years, and especially even recently. We were supposed to have a whole party up here on stage today, actually. We were supposed to have Hans Christoph Steiner from the Gideon Project, Lunar from the Tor Project, and from Debian. And we were trying to get somebody from who worked on the Gideon system in Bitcoin up here too. Unfortunately, for various reasons, several of those people couldn't make it. And Lunar especially is having some unfortunate circumstances, so we wish him a speedy recovery. But he has done a lot of this work for Debian. So for background, basically the idea behind reproducible builds is to sort of close the circle on this ethos or the promise of free software. The idea that the users should have all of the source code to correspond to all of the programs that run on their computer. And the original argument by the Free Software Foundation was this was for individual freedom, the freedom to modify, the freedom to understand, to work with the things on your computer. And the argument was extended to software security, that you can audit, and as with many eyeballs auditing all of the source code that people use, we can better understand as a community the vulnerabilities and the privacy properties and other aspects of the software that we all use.
Both from the point of view of knowing that the software doesn't have vulnerabilities, and from the point of view of knowing that the software doesn't have malicious functionality.
Right. Unfortunately, for the vast majority of free software projects today, the only proof that the binary packages that you download actually correspond to the published source code that you can also download is that somebody said so. Either this is a trusted institution, a trusted individual, an organization, or a collection of people. That ultimately is somebody compiles the source code and produces a binary that you download and you take their word for it.
So you have a sort of social or institutional connection where you go to a website and the website says, here's the source package, here's the binary package. But you as the end user don't actually have any technical evidence connecting these two, just the fact that they appear on the same website.
Right. And without information about the build system, even binary analysis, sophisticated reverse engineering techniques using IDA-Pro or even manual analysis of machine code, this verification is almost impossible. There's very large amounts of code differences. Even if you try to reproduce the build system as close as you can still end up with a large amount of differences, which we'll explain in later material. So as a result, it's sort of inadequate in really fulfilling this promise and fostering trust in the software's true functionality and security.
And we'll try to make this really concrete in a few minutes.
Now, the most common objection from hackers and members, such as probably many in the audience here, is, well, I'm the developer, or I'm a developer. I know what's in the binary because I download the source code and actually compiled it myself. And moreover, I'm careful with my machine, with my operational security. I know what I'm doing. Nobody's going to own me. Or maybe nobody cares to own me. Why should I have to worry about these hypothetical risks of somebody owning me some way, and why do they even care? To try and bring this into perspective and to add a little bit more rational thought into this, it actually turns out that as a developer, even though you may think your actions are benign, they still are interesting to adversaries. In fact, you're a very attractive target for someone who wants to compromise large numbers of people. Halvar Flake actually this year presented a very interesting work, offensive work and addiction, where he drew parallels between addictive behavior and addictive activity and this desire to compromise machines and progressively use what you compromise to gain more access and more access, and use them as stepping stones. And this has also been revealed to us through the Snowden leaks, and that intelligence agencies and institutions engage in this behavior too. They see a target, oh, we want to go after so-and-so, and so we're going to compromise anything that we need to get there. Google, Apple, any large infrastructure, any like software distribution.
And the temptation, because software is created with other software, to get the capability to compromise infrastructure, the natural thing to want to do is to get the capability to compromise other infrastructure and compromise other infrastructure. And there's a lot of transitive trust, because all of you, when developing, when hosting software, when creating infrastructure, are relying on other infrastructure for that, relying on other programs.
And there have been, even outside of the Snowden leaks, there have been known successful attacks by just hackers against infrastructure used by several free software projects. The Linux kernel, somebody had tried to institute a root privilege escalation vulnerability that was thankfully caught by Linus's careful custodian or guardianship of the canonical source code repository. Also Red Hat, Apache had their distribution servers compromised to distribute malicious binaries and packages. And just yesterday, ISC had their website compromised to distribute malware to the visitors. So this is something that isn't just a threat from state actors. This is very tempting for any attacker. So through the rest of the talk, we're going to spend some time trying to thoroughly convince you that these sorts of attacks against software distribution are very hard to detect, very possible, and it can be extremely harmful if the adversary has malicious intent. So to try and really drill this idea of this vulnerability, source of vulnerability home, imagine, if you will, the most secure computer that you could design or that you could use. Obviously, there's probably a lot of people who have a lot of opinions on this. Some people like OpenBSD will want to run SE Linux, will want to run AppArmor, will want to run GRSec kernels, probably disable Wi-Fi, Bluetooth, maybe USB. Maybe you keep the thing off the network entirely. Just keep it in a bomb shelter, behind in a Faraday cage. So in order to bring this back to reality, imagine you're in the realm of software development. Can your most secure computer that in your ideal scenario, can it still be useful for software development?
So we're thinking about a developer's laptop, or we're thinking about a build server used by a real-world mainstream software project.
So in the case of many open source projects, this computer is often networked. The developer, it could be a set of build servers that several people have access to upload their packages. It could be the developer's laptop that is mobile, moves from hacker conference to hacker conference, is left in hotel rooms, is potentially vulnerable to any number of physical vectors. And even in the extreme scenario where you have an institution that's capable of maintaining physical security over this computer, you still have to ferry data to and from it, often, via USB devices or cold storage. And there are several vectors, and just this year, Carsten Knoll showed that USB, through his bad USB talk, there are several vectors for USB devices to maintain persistence on so-called air-gap machines, even if you're doing things like reinstalling your OS periodically to try and wipe it clean. And then in more extreme scenarios, you'll have to run Windows on that machine to be able to build Windows packages. In the case of the browser vendors, they do what's called profile-guided optimization, where they actually crawl the Alexa top 1 million and get all that HTML and all that JavaScript unauthenticated and feed it through a profiler on a machine that outputs a profile optimization file that tells another machine that may be disconnected how to arbitrarily rewrite the resulting binary to make it faster. So you can imagine a piece of malware that targets that optimizer, causes a profile at a late stage in the build process, causes a profile to be generated that causes arbitrary rewrites of the binary to introduce gadgets for exploitation and malware.
So if you're thinking not just of the source code as a target of attack, but really the infrastructure that's used to produce the software, that's used to produce the binaries as a target of attack, it's a big deal.
So this gets even worse. So take your most secure computer that you've been thinking about and imagine that not only are all these attack vectors possible, not only does it have to be used in these risky use scenarios, what if it's extremely valuable to compromise? What if compromising that computer gets you access to hundreds of millions of other computers? What if it gets you, in the case of the browser vendors, what if it gets you access to every bank account in the world, in the case of software that runs the financial system? What if it gets you access to every Windows computer in the world? And maybe you're not even the adversary is not even compromising Microsoft here. Maybe they're just compromising a popular dependency for Windows development, or something like Flash that's on 95% of Windows computers. Or in the case of Debian, Red Hat, and Ubuntu, every Linux server in the world. And then this goes on to, and then you can carry this thought experiment further. If you think about how much that computer is worth in monetary terms, if you're targeting servers, remote O-Day against hardened servers can go for $100,000 or $500,000 or more on the black market. If you're talking about, in the case of the Tor project, censorship infrastructure, Iran and China spend hundreds of millions of dollars a year on their firewalls, so disabling something like Tor can be potentially worth even more. And if you're talking about financial software, just a small example is the Bitcoin community. The current market cap of all the Bitcoins in circulation is $4 billion. Many of those are offline, obviously, but you obviously still a very juicy target. So I don't know if you want to speak about your conversations with.
Yeah, so I'm not directly involved in the Bitcoin development community, but from what I've heard, and I'm sorry that we don't have Bitcoin developers on stage to describe this firsthand. From what I've understood from talking to Bitcoin developers, this became a really concrete concern. Certainly as the amount of money involved in the Bitcoin ecosystem has grown. The idea is basically that the Bitcoin transfers are irrevocable. And so if someone can cause a Bitcoin client to issue a transaction, they can steal someone's Bitcoins anonymously and irreversibly. If you imagine malware in the Bitcoin client itself, the malware could sort of wait for a year and then do this at a certain point. And someone might say, oh, the developer put that malware in there to steal everyone's money because the developer obviously had the necessary access to do that. And the developer might say, no, someone hacked into my machine. It wasn't me, it was a third party. Well, people might not believe the developer, right? The developer has an incentive to lie about that. And so really, the developer's inability to sneak something into the code or to have someone else sneak something into the code late in the development process is a source of protection for the developer. And I think this really stimulated the Tor project thinking about this and the analogous consideration.
I was very concerned, actually, about our build engineers traveling through various jurisdictions with potentially with their build machines and cryptographic material and the laptops that produced a lot of our packages. As we're a very distributed organization, we don't have a lot of centralized, secure, physically secure network offline computers to be able to build. So we had the situation where our build engineers were traveling and might be subject to coercive risk, demands to put backdoors in the software. And so I really wanted to eliminate that completely as a possibility.
So I wanted to get people thinking very concretely about the relationship between source and binary as a vector for introducing bugs and vulnerabilities. So I have a couple of concrete examples just to sort of stimulate thinking in this area. This is a real bug from back in 2002, so this bug is now 12 years old. I mean, it was fixed in 2002. This is a very typical bug, a fence post error in the OpenSSH server. And so the idea is that the programmer wrote greater than instead of writing greater than or equal to, because this is something that was counted starting from 0, and the programmer was thinking in terms of counting from 1. Totally common fence post error. And so this is the fix that was applied where the condition should have been greater than or equal to instead of greater than, right? So it got fixed. So what kind of change did this produce when the fix was applied? Well, I went through the assembly and compilation process to look at this because I had a hypothesis about how big it would be. And in fact, the hypothesis was right. The difference in the binary is going to be a single bit, fixing this apparently remotely exploitable bug. So just looking through, the compiler, in one case, in the vulnerable case, generated an Intel jump if less or equal. In the fixed case, the compiler generated jump if less. And if you look at how those opcodes are represented, it's a difference of a single bit. There's also a corresponding case for greater than or equal versus greater than, which is also a difference of a single bit. Right? So this is a small excerpt from the assembly code of the OpenSSH server from the version back in 2002. On the left is the vulnerable version. On the right is the fixed version. You might not notice the change. It's pretty small. That's the change there, right? And when we compile it, this is a short excerpt from a 500 kilobyte binary. And that's the only change in the binary as a result of fixing this remotely exploitable bug. So what that means is you have a particular concrete case where if you can flip a single bit in a binary, that makes the difference between remotely exploitable or not remotely exploitable bug being present or absent. Now I also have a demo that I thought would also make the sort of trust in the laptop issue concrete for people. So I wrote a kernel mode rootkit just to think about how much do you know about what your system is doing when you compile something. So I have here a program that does some, is that big enough for people to read? I have here a little C program that does something really important, which is that it adds two numbers. We could take a checksum of the program, maybe a more cryptographically modern checksum, right? So this is the source code of this program. We could look at it in an editor. Right, so it takes two command line arguments and it adds them and outputs the result. So I'm just going to compile that. And what numbers? I'll add 17 and 23. Okay, 17 plus 23 is 40. So I'm just going to install a rootkit on my laptop. Okay, using the handy install rootkit command. So I hope you've memorized the checksums there, because I'm just going to go through this process again and take a look at the code. Right, so there's the code. Checksums are still the same. Okay, there's the source code. And let's add 17 and 23, having compiled this. I'm gonna give you up, I'm gonna let you down, I'm gonna run around. So this is the special Rickrolling rootkit. And so just to point out quickly what this particular rootkit is doing. If I make a copy of the cat program and look at this code, it's totally normal. But if that copy of cat were called CC1, which is one of the internal subprocesses used by the C compiler, then the kernel would notice that it was the compiler trying to read this source code as opposed to some other program. And it would actually cause it to open a different version of the source code. And so that means that what this rootkit is doing is introducing a difference in the content of files just at the last moment as you're actually compiling them. So if you were to look at the source code using any kind of tool on your system other than the compiler, you would say, oh, my source code is totally correct. If you look at it with SHA-1 you say, my source code is totally correct and unmodified. And there are no changes on the disk, right? The source code on the disk is correct, the compiler on the disk is correct, the kernel on the disk is correct. All of the modifications are happening in RAM, and then you're getting a modified binary at the last minute as you actually compile it. And the compiler is faithfully compiling what it's given. It's just that, in this case, the kernel isn't allowing it to access the proper source code. It's accessing a slightly incorrect version of the source code.
Now, of course, that was just a very basic proof of concept rootkit. I mean, you can't expect to defend against an arbitrary rootkit by renaming your compiler to something else and then hoping that you'll be able to, or renaming your editor to something else and hoping you'll be able to actually see the true source code. A more sophisticated rootkit could, of course, inspect the virtual address space of what claims to be the compiler, make sure it actually is the compiler, and only act in those cases.
Yeah, and so the basic idea of this kind of rootkit is to say, we want to produce a specified change only in the binary of a very specific program, only at the moment that that's actually compiled, so that the developer will say, okay, I compiled it myself, I checked the integrity of everything myself, this binary is good, right? Okay, so I think it's going to be very hard to defend against this if you allow the possibility that the server or the laptop that you use to actually make your binaries may have been compromised at some point, or may be compromised at some point in the future.
So yeah, so the idea behind build reproducibility is eliminating that developer's laptop or any build machine as a single point of failure, basically bringing some science into software development for once. If you give anybody around the world the ability to take the source code and produce an identical binary to the one that's being distributed, you then require the adversary to basically have to compromise everybody.
And this addresses a pretty wide range of threat models that relate to the compilation process itself. In the sense that it's not just about whether the developer is malicious or whether a third party is malicious or whether the developer is under coercion, right? It's a wide range of things. Any kind of particular threat that might result in a discrepancy between the source code and the binary.
Okay. And it also turns out that sort of development practice is actually very useful as sort of a canary in the coal mine to help you know if there's something wrong with your build machines. If builds stop being reproduced faithfully, something's wrong with the machine. Either it's having a transient hardware failure or some issue with the build process, or perhaps it's been compromised. So you get that external validation for free, basically, from your developer and enthusiast community. So how hard is this? Well, it depends on what you're trying to compile. For sophisticated, very large software projects, especially ones that have custom scripted portions of their build process, it can get quite involved. The most obvious differences are if the build machine is configured differently as different software. You have either different compilers, different optimization flags, different header files, different library versions. But it can also extend to build processes that pull in metadata from the system. It's very common to include the build host name, the kernel version, the
file modification times. Maybe.
File modification times. It turns out the debugging formats for ELF actually often include full paths to the reference to where the source code is expected to be. The container formats such as tar and zip and jar and APK end up with metadata and file system source data. You end up with signatures. You have entropy that can be introduced by signatures if you have any signing process as part of your distribution built into the packages.
You probably don't want to allow third parties to reproduce your signatures.
Right. Obviously, you want to keep some things secret, such as your key material. Test-driven optimizations is another problem that the browser producers are grappling with, as I mentioned earlier, where they have to try and tune their machine code for the most popular websites. So who's doing this? I think the widest, most public institution that first made this as a process for all of their builds was the Bitcoin community. However, back in the 90s, the Free Software Foundation was concerned with this property. And I mean, if you trawl through the ancient documentation, man pages, pre-info era even, you see references to, well, how to do deterministic linking with R and LD. So the toolchain has been thinking about this for a while, but it just hasn't been deployed in practice.
A lot of the toolchain reproducibility work from the 90s was done by Cygnus. When Cygnus was maintaining the GNU toolchain, they actually had some tests that involved getting reproducibility within the toolchain itself, like compiling the compiler twice and making sure that the output was the same. John Gilmore said that turned up dozens of bugs which Cygnus managed to fix in various parts of the toolchain. So it's good for other testing aspects. But yeah, there was this concern in the GNU toolchain in the 90s, and unfortunately it didn't really spread throughout the operating system and applications world.
Thankfully, that's starting to change. The Tor project, as I said, was inspired by Bitcoin to use the Gideon system, which I'll get into in a bit. The Guardian project is also working on making sure their packages are reproducible. Debian has somewhere around two-thirds of their packages currently already reproducible, at least in one of the branches, either unstable or testing. Red Hat is working on this in Fedora. F-Droid has a very neat build verification system in the works, which we'll describe in a bit. Mozilla is interested, and we hope that developers in the audience and who view this talk online will be inspired to try and do this for their own software projects. So how does Tor Browser do this? So I'm the, technical lead on the Tor Browser. And for those who aren't familiar, basically we have a branch of Firefox. We have about 40 to 50 patches on top of Firefox for third-party tracking and fingerprinting defenses and Tor integration. We have a Tor client and an add-on that helps make configuration of Tor. It's very simple for novice users. And then we have these things called pluggable transports, which are actually separate binaries that obfuscate the traffic for the first hop to get around censorship firewalls in China and Iran and elsewhere. And we have a couple of add-ons as well, no scripting, HTTPS everywhere. So the build system, we now use Gideon, which was developed, as I said, was developed by the Bitcoin community. Basically, well, I'll get into what Gideon is in a bit. The output from Gideon produces a full package set and incremental update files as used by the Firefox updater, for which a single SHA-256 sum file lists all of the hashes of all the individual packages, and those SHA-256 sum files are GPG signed by all participating official developers. We also were very interested in supporting anonymous verifiers. So the inputs are actually downloaded by default over Tor. So it's very hard to tell who is a verifier. We encourage anybody who finds discrepancies in our builds to report them pseudonymously in our bug tracker and not reveal necessarily who they are, so that we can make it even harder to compromise all of the extended community of verifiers.
So no one can make a list of all the machines that are testing the reproducibility and correctness of the build. It
was also very important for us not to have it require dedicated hardware, especially not everybody. We don't want people to have to purchase a Mac and a Windows machine just to be able to reproduce those builds. And we wanted all the build components and dependencies to at least be free as in beer, so at least interested individuals could download them even for the proprietary platforms. For example, the macOS SDK is free as in beer. You get binaries, but you don't get source code, but we're still able to use that. But the Linux tools are, of course, all free as in freedom. And as far as what those components look like, on Windows, we cross-compile, and on Mac, we cross-compile from a Linux host. We use MinGWW64 for the compiler on Windows. We use Py2xe for the Python bits and Nullsoft for the installer. We have a couple of cross-compilers for Mac that were graciously provided by Ray Donnelly. He's a very excellent, I believe he works in video gaming, the video game industry, but is very interested in making sure he can compile for iOS and Mac from his Linux machine. And to produce DMGs, we use makeifs and DMG. And for Linux, we use some newer versions of the toolchain, which we compile ourselves for reasons I'll get into in a bit. So what is this Gideon Beast? Basically, as I said, it was developed by the Bitcoin community. It's a thin wrapper around the Ubuntu virtualization tools, and that's QEMU, KVM, and LXC, the Linux containers. The compilation stages are represented in what are called YAML descriptors, which are individual files that specify an Ubuntu version and an architecture, a package list to install on that VM, a list of Git repos to clone, and any additional input files that go in. And then an inline bash script that just gets run on that virtual machine as your build script. And then these descriptors can be chained. So the input files go into the compilation process to produce output files, and then those output files can go in as input files to the next stage. So what does this provide? Obviously, any sort of scripted virtualization container or container system can help normalize host name, username, your build paths, your tool versions. if it's a fully virtualized system, your kernel and uname output, and then through fake time can fix some timestamp issues. It doesn't require, as I said, very important to us, it doesn't require dedicated build hardware. It can be run on any Linux machine that is capable of running Ubuntu in some form, and we're extending that to Debian very soon. It authenticates your Git-based input for you, and it integrates with the fake time Linux command line utility for spoofing timestamps. So some problems that we ran into with Gideon. To start, it's Ubuntu only. We've put some work into making it possible to be hosted from Debian, so you can launch your VMs from a Debian system, but they're still right now can only be Ubuntu guests, so we're still working on that. If you're using non-Git input, obviously it's named Gideon after Git, you have to provide additional authentication for those packages.
To explain how you know what the input is,
right,
or how you identify the input.
Right. And partial compilation state is a little tricky. Basically, it creates a base image, and then you have for every compilation run that you do, it creates a qcow2 copy on write secondary image that gets written to for any modifications. And normally that secondary image is destroyed for each stage to keep the base clean. But you can hack around and sort of play with descriptor stages, and I believe there's a branch that allows you to use that secondary portion to do incremental builds where, say, you modify a source code file in Tor, you can then resume the compilation process of just Tor. But it is still kind of clunky and time-consuming to sit there and wait for these builds end-to-end to see if they match. It took me about 2 months of work to get Tor Browser building for all three platforms reproducibly, and most of that was spent sitting around waiting wall clock for the builds to complete. Maybe you should have done the sword fighting. Oh yeah, the XKCD. Well, compiling. No, I did a lot of that in various forms, don't worry. So this means it's sort of kind of janky. Sometimes there's process management issues with QEMU KVM. You can only have one QEMU slave or LXC slave at a time. And it doesn't solve everything. So in the case of Firefox, where you have Python scripts pulling in things from all over the file system, assembling them into jars and zips, you have all sorts of file system ordering issues. So interestingly, the readdir system call in POSIX, the order of your directory listing is not specified. It basically comes out in whatever ordering the inodes were written to on the file system. So that means on machines of different speeds, if you have a compilation process, especially running in parallel and things are happening at the same time, the order of those files getting written in that directory can be different. And then a script or zip or tar that pulls them all in is going to end up with ordering issues, and the binaries are going to be different. So the answer to that is, of course, you sort it. But then you run into the problem that different locales sort things differently. So you have to make sure you set the locale explicitly to specify your sorting order. We ran into uninitialized memory. So as Seth said, there were tests in Cygnus that made sure that the toolchain had no reproducibility issues of its own, but on some forks, like the cross-compilers, these tests weren't being run, and MinGW W64 introduced a regression where a structure field, or the padding in a structure, wasn't being properly memset to 0, and so we were getting random bytes in parts of our Windows binaries. We had a similar problem in the creation of the DMG on macOS.
It would be awesome if those random bytes turned out to be meaningful.
Oh yeah, no, we spent a long time trying to figure that out. I actually wrote a sed script, a little scriptlet, to look for the surrounding bytes and then just bang out those bits to like 23, 23, 23. And people were shocked and horrified at that, enough for an anonymous contributor to show up and be like, no, there's a problem in binutils, here's a patch, stop doing this. So that was kind of nice. Thank you, Bob Nom Nom, wherever you are. Or Scruffy. A round of applause for Scruffy, everyone. He's pretty awesome. Or they are pretty awesome. That's our anonymous Tor bug reporter, who is possibly a collection of people that reports all manner of interesting bugs and submits patches as well. So time zone and UMask obviously can leak deliberately generated signatures, entropy. And LXC and probably Docker containers will have this problem as well for people who are experimenting with other ways to do this. They won't wrap your kernel. Where there's a build issue with libgmp where it actually inspects your current CPU and says, oh, I'll build with these optimizations for you. You know, we know you have this type of CPU, we'll just build with that, unless you say, no, build all the optimizations. And then, so you get differences in different CPUs. And LXC still has memory initialization issues that we have not fully tracked down yet on some platforms. So as Seth was talking about, we wanted to also protect our developers from targeted input delivery. So we want to make sure that nobody could compromise the way we download inputs and say, oh, that looks like the download for Gideon. Let's feed this malicious source code. And now when they run the configure script, we can compromise the build process that way.
Or that looks like a download for Gideon. Let's try to compromise that person's laptop.
Yeah.
So that we can cause it to say, yes, everything compiled properly.
And some projects don't even provide signatures for us to do this verification, so we have to actually hard code SHA hashes in the build process, so in case their servers, their file FTP servers or HTTP servers are man in the middle or compromised, that can't be used to affect us, or at least we'll know and see that the SHA is different before running the config script. And an embarrassing list of projects actually have very weak or no signatures. OpenSSL for a long time was signing with MD5. Now they sign with 12 keys. One of them is owned by Frodo Baggins of the Shire, or at least that's what the email address is. There's another name on it too.
The software authentication problem in general is quite bad. My former colleague from EFF, Chris Palmer, wrote a piece about trying to authenticate a PuTTY binary. You know, PuTTY is kind of important because you might use it to log into all your servers. And they have a non-HTTPS download, and they have a HTTP delivered signature that's on another domain. And yeah, software authentication in general is pretty rough out there.
Yeah, especially in the Windows world, I think, as well. But luckily, I think Firefox is probably one of the most complicated things in the world to try and build this way. And as a result, our build process is massive and scary. Most things aren't that complicated, especially, it turns out, Android. Most of this material was prepared by Hans Steiner of the Gideon Project. But he has been working on reproducing Android packages. And because they're mostly pure Java and the JDK versions are standardized, it's actually fairly straightforward to produce a reproducible Android package, at least to the point where the signatures match. So for APKs, I guess Google realized that the jar format based on zip can pull in all sorts of metadata and have ordering issues. And as a result, the APK actually only signs the contents and the manifest that describes the package and doesn't mess with the container. Now, the Langsec people in the audience probably are all cringing, like, oh, now there's this discrepancy between verification of can exploits be introduced by what's happening at the zip layer versus what's happening at the APK signature layer. And I think the answer is probably yes. In fact, I believe there was a very good talk last year on this possibility where they demonstrated that those sorts of discrepancies can introduce Turing-complete machines that you can use to execute what you want based on just the discrepancies between the grammars of different parsers. That was
Depends on how the parser is used.
Yeah, right. Depends on the nature of how you're using that. But so nonetheless, F-Droid is moving towards using this property to allow developers to build their packages locally, submit the binaries with their local key signature to F-Droid, and as well as a source code URL. And then the F-Droid verifier can recompile the source code, run verify, which takes the signature from the developer's binary, attaches it to the F-Droid built binary, and sees if it verifies still. And if so, then the verified binaries can be published with the developer's signature. So now you solve the problem with F-Droid that currently exists, where you're implicitly trusting, whoever uses F-Droid is implicitly trusting F-Droid and their ability to maintain control over their key. There's a single F-Droid signing key currently, but this reproducibility system allows you to have to compromise both the F-Droid build system and the developer's laptop.
So let's just think concretely again for a minute about what the world would be like without this property, or what the world has been like without this property. So without this property, you have all these developers who have their laptops and they're making these APKs, and then they're uploading them into the system, and then people are saying, great, it's open source. So everything's fine, and we'll just give the APKs to everyone in the world. And that also, just to think further concretely about something that Mike is about to come to, that's the way that Debian worked until just a couple of years ago. That each individual Debian developer had the ability to make a binary package upload that was created on that individual developer's laptop. And what you had was that developer's word that that binary package matched the source package. And you didn't have a technical mechanism that was under the control of the Debian project. You just had uploads of binary packages by thousands of individual Debian developers that they made on their own laptops. So having this for any kind of package repository is really a major shift in the kind of assurance that end users can get about where their binaries are coming from and how their binaries were produced. It's really quite meaningful.
So the Debian effort was, I believe, spearheaded by Lunar and Holger. And they include, so there's so many different kinds of software, but obviously packaged in the Debian universe, that they had to patch several aspects of their build system and supporting utilities in order to make sure everything was reproducible. I mean, this list here, deb helper, CDBs, depackage, this Python tools, Java tools, even Octave apparently had to be patched and is involved in some packages build system. They have a wiki page that describes all these problems in detail and is very well informative and invites anyone to help out with that effort as well. And as a result of this, I believe they have somewhere around 60% or 2/3 of their packages currently being built reproducibly. And they have a cool little Jenkins graph that shows that, slowly has been going up and to the right for the past 6 or 9 months since people started taking this effort seriously, and all the individual package maintainers have been working to make their packages reproducible.
And that really protects Debian developers in much the way that you described that the Tor reproducibility protects Tor developers. It really produces a much diminished incentive to compromise a Debian developer's laptop or to try to coerce a Debian developer to do something improper in a software release, at least at the binary level.
Yeah, and formerly we had the situation where you could find any one of 1,000 people who just left their laptop at a hacker conference lying on a table one day, wasn't paying attention, and allowed you to stick a USB key or something in, and then you could compromise the entire Debian population just from one of those 1,000 people or so that were building packages. And now that's no longer possible. And it's getting to the case where you won't even be able to compromise their central build system anymore.
Or at least that it would be detected.
Right. Yes, in a way that you can send packages. Now, they took a slightly different approach to expedite this process. They strip out differences that they found common to many packages. There's actually a strip determinism helper that removes timestamps and handles common issues of file formats and normalizes these things, and basically alters those. And it's used, I think, as a large part of what got Debian so far in terms of all of their packages being reproduced. But because it modifies the binary, it itself can be as a target for compromise and another single point of failure. And you introduce this trusting trust attack, where if you can compromise the things that build chip determinism, that can be used to propagate a backdoor. For those who aren't familiar, the trusting trust attack was first described by Ken Thompson in the 80s in a paper, his famous paper, Reflections on Trusting Trust. What he did was took the C compiler and wrote a backdoor in source code that went into a binary version that went out in one release, and then removed that source code from the compiler source code. But the backdoor was of such a nature that, like what Seth demonstrated, it could insert itself into the compiler source code.
So it's a self-propagating backdoor that's only visible in the binaries and never visible in the source, but that can propagate itself through multiple generations of the compiler. And that's, still a considerable concern about the integrity of our infrastructure. And there's research, which you're about to mention, by David Wheeler describing one means of addressing this. And Wheeler actually found that the same attack was actually described by Air Force researchers in 1973. and that they said, oh, someone could make a self-propagating compromise in the software development toolchain, and then we wouldn't notice, and then all of the things that we built could be compromised. So this is a concern that people have identified back in 1973. And the Air Force researchers suggested that this would be a powerful tool for espionage that someone might be tempted to do. And I think that's still the case.
Right. So David Wheeler actually found that what you can do is you take two independently developed compilers, and you only need the binaries for this. They can be, one of them can be proprietary compiler. And then you use those two compilers to compile the source code of an open source compiler, and you produce two more binaries. Now you have two binaries, one of which may or may not have a backdoor. And now you use those two compilers that were compiled from the same source code but with different compilers to compile that same source code again to produce two more binaries. Now those two binaries should be identical if there is no backdoor in, unless there's the same backdoor in both of the binary compilers or there is no backdoor.
So David Wheeler's thesis is really great if you like saying the word compiler.
Yeah. So Bruce Schneier has a very good description of this and that describes all the security properties. But the really important property is that now that Debian is working on reproducible builds, it turns out that, as Seth demonstrated, this sort of backdoor can propagate between the kernel and the compiler, or the compiler and userland tools, or the linker, or anything on the system. And Dr. Wheeler only proved that his two compilers didn't have backdoors. He did not rebuild an entire build environment.
So you also have to trust the operating system.
Right. We still he trusted the operating system in that experiment and concluded there was no backdoor in GCC. But we still don't know if there might be a backdoor that is capable of propagating between the kernel and the compiler. But with Debian's reproducibility, what we can do now is, if we have a base system that can be cross-compiled to all architectures and is still reproducible, you can take the ARM build, the PowerPC build, the MIPS build, the Intel build, and you can take the herd kernel, the KFreeBSD kernel, and you can have them all cross-compiling and verifying each other. And now you force the adversary to be very forward-looking in a way that they would have to have anticipated. Oh, we need to have a self-propagating backdoor that has so many copies of itself that can actually survive.
That it's able to infect every architecture using every tool and survive by infecting every architecture in a compatible way.
And it turns out you can also throw in proprietary compilers using Dr. Wheeler's technique and then force the adversary to have to have compromised those as well.
So we're getting very close to being able to actually do this kind of assurance for essentially the first time ever.
Yes. So we're almost about to be able to prove that the integrity of software to the level of the hardware, which then... which, as you know, is then a whole new set of turtles all the way down. But we'll get that too. I think Bunny Wang is still working on that one.
Did you want to talk about the...
Oh, yes. So then if you want to talk about the software distribution problem, I think you
Oh, well, I think this could be a whole other talk, but I mean, there's also this problem about when you distribute software updates to people, how do you know that everyone is getting the same update? And I think that's a pretty significant problem in its own right, because this is talking about how can people who check verify that binaries were produced from a particular source code version, but we also have this other family of problems about, well, is everyone actually getting the same update? Or could, for example, the Tor project put out one version of the Tor browser and another version of the Tor browser and have a malicious backdoor in one of them and give that to a small subset of users? Perhaps in a reproducible way, but still in a way that would compromise those users. So I think there's actually, for the concept of software transparency and software development transparency generally, there are actually a few other problems on top of this. Not just making sure that source code and binaries match, but actually making sure that everyone gets the same thing.
Now the core problem here in a theoretical sense is one of distributed consensus. Everybody has a potentially different view of the internet. And we're seeing this more and more as there's more censorship regimes and interception hardware. Just because somebody else can download the canonical Tor browser from one location doesn't mean that somebody in China, when they try to download it, they're going to necessarily get the same packages. So in order to try and ensure this, one of the things that we're planning on doing is having our updates authenticated in addition to signatures by the Tor consensus. So there'll be a URL with a hash that itself contains a list of the hashes of all of the update files for the browser. And we can further strengthen that by either storing records of the Tor consensus in the Bitcoin blockchain, or using the Bitcoin blockchain directly, or using something like certificate transparency to record the Tor consensus or the package archives. And further ensure that everybody sees essentially the same consensus view of not just the Tor network, but also our packages. So we have some links here that are also in the slides we've just uploaded about an hour before the talk to the events page. So if you're interested in working on this problem for your own software projects, there's some useful things. The Tor Browser design doc has a section on build security that describes Gideon again. The F-Droid verification server, again, that's not complete yet, so if you're interested in Android development, I'm sure they'd love some help making sure that all the packages are ready to be used with this system. Debian also, I'm sure, would love your help with any packages, making them reproducible. And then if you would like more information on the diverse double compilation and how we can get to true software or binary integrity all the way down to the hardware, these two articles are excellent. Bruce Schneier gave a very succinct description of Dr. Wheeler's double compilation, and the LWN article actually points out, oh, well, you need to do not just the compiler, but the whole operating system.
I would also recommend, Mike wrote some very readable and very useful blog posts on the Tor blog about the motivation for all of this and about how the Tor project succeeded in doing it. It's much the same material that you've just heard, but if you want to see it in written format, there are a couple of great posts on the Tor blog. And again, Thomas Dellion's piece, Offensive Work and Addiction, talking about the incentive that an attacker would have to compromise infrastructure as a means of compromising infrastructure as a means of compromising infrastructure. And the sort of addictiveness of, hey, I can get more and more power over information technology as a whole because of the trust relationships between software projects.
All right. There's our contact info if you want to Gmail us or contact us in any way. I guess we can open up for questions. If you want to line up at the microphones here, if anybody has any questions for us. We have about 5 minutes.
Yes, thank you very much. First, are there questions from the internet? Yes, can you approach one microphone?
One.
If you leave, please take all your trash with you and also take other people's trash with you if you see it lying around. And approach one of the microphones if you have questions.
A little noisy. So, I have one. The first question: if a developer computer is compromised and got a bit stick, so an adversary could change a small part of the code to make the code vulnerable to attack. In this case, the code could be compromised from the very beginning. Why would reproducible build help to see this manipulation as a computer would have the compromised code?
I guess that's referring to source code?
I think so.
Yeah. Do you want to try to address that? I mean, I think one of the problems that we really do have in terms of people introducing vulnerabilities into systems, if you look at the obfuscated V contest or the underhanded C code contest, there's an annual contest for writing malicious source code that can pass an audit. And it's very scary because you look at some of the results and it's like, okay, this code here has a malicious functionality that's as follows, and here's the source code, can you see it? And people have managed to make some that are very hard to see in the source code.
I mean, I think the best, simplest answer is the one that the free software community always gives, is that many eyes. We hope that by having the software open and having, especially incentive programs, vulnerability reward programs sponsored by people who rely on that infrastructure for critical things, to sponsor disclosure, We hope that those sorts of mistakes can be found. And also things like Git, better source code integrity policies. There's a lot of projects that just throw tarballs up on FTP sites and don't have any authenticated sort revision history. That's very dangerous, I think, for this sort of attack. So things like Git and other distributed version control can help prevent that. You have to compromise all of the Git repos and get it in there, or there's at least a commit record in all of them that shows this change being introduced.
One question from microphone number 2.
Griffin.
Very bright. I had a question where you say that you hardcode SHA-256 hashes into the build process to sort of verify that upstream is okay. Have you considered the possibility of actually adding in like signed, Git commits and then having something in the build process that will verify those based on hard-coded keys?
We do. We do both. We have the key rings for all of the Git repositories that actually sign their commits, and packages that sign their source releases. So we use those signatures to verify the inputs where we believe they're strong, and if we think they're sketchy because there's 12 developers who can all sign the same thing, or they sign with MD5 or whatever, that's when we introduce the SHA hash into our repo. And we also sign the Git tags that we build from in the case of Tor Browser. So when you check out something to build for an official release, it has my signature or Georg's signature on that actual commit.
Okay, thank you.
Okay, another question from the internet, from microphone 3.
Question number 2. What procedures are there when there is a failure noticed to compromise keys? Blockchains are hard to roll back multiple steps.
Having trouble interpreting the question. If there's a key compromise?
What procedures are there? Is a failure noticed to the compromised key?
It depends on which key. I mean, there's a lot of key material. There's the keys for the inputs.
I believe the question get in the direction of what happens if the key is compromised.
So that is why we want to extend the software update authentication to the Tor consensus and the Bitcoin blockchain. So keys that sign the software that you download, you'd have to compromise all of the builder's keys because it's now multi-signed. But if you manage to do that, we hope that the Tor consensus, which is itself signed by a different set of keys and can hopefully one day be authenticated by another consensus process like Bitcoin blockchain, all of these systems provide security, like layers of security, that hopefully someone somewhere can say, hey, this signature for this package claims to be a valid signature, but yet is signing something that is not a hash that was published elsewhere. So far that hasn't happened. It's possible it has happened and nobody has managed to tell us, but we haven't seen any evidence of that with the Tor software at least.
Okay, one more question from microphone number 2.
Hi, great talk to both of you. My question is for Seth. Is the install rootkit program open source anywhere?
I knew we were going to get this one.
So I wasn't really planning to publish that. We did give a version of this talk at Mozilla, and one of the Mozilla developers apparently actually re-implemented it. So apparently there is a version from one of the Mozilla developers. I'm not sure what it's called, but it was actually out there and has this functionality.
But yeah, this is basically, I think there's a FRAC article from the 90s that describes the techniques. I mean, you're hooking the open system call in the kernel to see if the process that's opening the file is named CC1. So it's a really naive implementation of this sort of thing. Again, a real sophisticated rootkit would do things like also inspect the current process address space to make sure it really is a compiler and other such things. So,
I mean, I know that people do want to like rickroll their coworkers and so on. So if someone can convince me that there's a real gap, that existing rootkits are just not suitable, then we can consider cleaning this up and publishing it somewhere.
So another question from over here.
Hello. What about the role of the linker, and which one is usually used of the two linkers from binutils?
I believe we started, I didn't get it, actually describe it in detail. I believe we switched to the gold linker, which is I think the GNU linker?
Yeah, that's the new one.
The new one. So it turned out the old one had an issue with the implementation of SHA-1 on 32-bit machines, where if it was taking the build ID for debug link to link the debugging symbols to a stripped binary, you can have these things in separate files, and then there's this build ID that contains the SHA-1 of the build to associate the two. That SHA-1 implementation in the old linker had some sort of issue with very large files. We ran into it on libzool.so, possibly because with debug symbols, that beast ends up larger than 4 gigabytes. And we ended up with random values for that SHA hash, not different values than the official SHA hash, but random values for that SHA hash. So we had to switch off of the old linker and start using the new linker. For that reason, I think the new linker also has better memory overhead properties for linking very large things like libzool, the Firefox library. So,
okay, one more question from the internet.
The third question, how do you propagate a backdoor among compilers? You can use fingerprints, but they are not future-proof, and detecting if a piece of code is compiler is quite infeasible from the information theoretical POV point of view.
Yeah, so the basic point is that it might be implausible to have a real-world backdoor that propagates itself through very heterogeneous code bases, especially compilers. And I think that's absolutely correct. I think that the more realistic scenario, if you look at something like Thomas Dellion's presentation, is actually sort of an actively maintained backdoor, where someone is compromising not only code bases, but servers, and is periodically logging into the servers and manually intervening in the development process. So I think the real threat scenario would be that someone has compromised developer workstations or build servers inside various organizations and projects, and periodically adjusts the backdooring in order to maintain access. That's the sort of...
Whereas you don't get, and you can even get that ability against air-gapped computers. You just keep seeding the parking lot with new USB keys that have the malware on it. And they propagate through all the computers until somebody plugs in the USB key that goes into the build server. But you don't get that property with the compiler because it has to be baked in that compiler once, and then all of the binary versions of that rootkit have to be there. And you get, in the diverse double compilation, you actually get to use old compilers. So you can go back into your archives and pull out a compiler binary from 1983 and use that as long as it implements the subset of C that GCC can compile GCC, you can use that one. So the adversary would have had to gone back in time to 1983 to get their multi-architecture support introduced for an architecture that was developed later, like, I don't know, what would be ARM? Is it ARM a new one?
So I think the intuition of the person asking the question is that it's very difficult for a backdoor to propagate without human intervention through heterogeneous compilers. And I think we completely agree with that. And in fact, that difficulty becomes a part of the safety strategy. And that the real attack strategy is probably more manual on the part of the attacker.
Okay, as we are running out of time, one final short question from here, and please a short answer.
Yeah, I would like to know how well do multiple thread works with reproducible builds? So if you use more than one core to build your binary, is this build in general still reproducible?
That is where you run into things like the file system ordering problem, where the different make threads or processes will be writing files into the directory in different orders between different machines, depending on how many processes you're running. So we do use multiple cores in the Tor Browser build process, and we solve that through sorting. We sort everything before we make any archive of tar or zip or jar during the build process. And that takes care of that.
Thanks.
Okay, thank you very much. Please give another round of applause to the speakers.